All right, let's get started. I brought a very warm coffee today, and I think that was somewhat necessary given the meat locker of a room that we're in this morning. I come in and the temperature in the room is 65, and I try and turn the heat up, and it said the little controller says standby. So it's now at 67, so brace yourselves for the heat wave. I've got the sign-in sheet going around. Let's talk about logistics and timing and whatnot. So you all have a homework due on Tuesday, right? So what I generally like to do the day before a homework is due, this is our last lecture, and I think I mentioned this on Tuesday, but I like to open the floor for questions. So hopefully you all have taken a look at the homework and what have you. If you have any questions about the homework, you know, I'm more than happy to address them. Remember, I'm not going to bite anybody's heads off or, you know, people ask questions. I mean, please feel free to ask, you know, whatever questions you have because, you know, this is the time. Are there any questions on homework 1? Because y'all are almost done with it right now. Yes. Yeah. Yeah, just put like if there's 4 pages, do 1 out of 4, 2 out of 4, 3 out of 4. And honestly, I just do that because if I lose a page or if a page goes missing, then we'll know. So, yeah. And I also I have this. I pulled up the syllabus. I do like a cover page, but pretty simple. All I want on it is just, you know, your name, you know, Engineering 216, homework number 1, and, you know, the day you're turning it in. A lot of people just print off the assignment and put their name on it. That's fine too, because it's got all that on there. So if you want to do that, that's fine. There, yeah. So any other questions? Anything else? All right. So what we're going to do today is we're going to begin. Move that out of the way. What we're going to do is we're going to, you know, we basically finished our fundamentals in the class. We've got a pretty clear definition, hopefully by now, of what is stress, what is strain, and what we're going to do is take, and how they're related. So what we're going to do is we're going to take those definitions and we're going to start to address typical types of problems that we deal with as civil and mechanical engineers. And so we're going to start with an axially loaded member. We're going to take axially loaded members and just sort of run the gamut with them. So I want to go through some of that, that theory a little bit. So hold on. All right, let me plug this in. Come on. There we go. Now, we start with axially loaded members in here because axially loaded members are the easiest place to begin because we've pretty much already derived in one way or another all of the formulas necessary to start attacking axial loads. So, you know, what we do is we basically say, all right, we start off with Hooke's law, okay? So we start off with our fundamental relationship between stress and strain, okay, right here. Let me erase that better now. Okay? And we say, all right, well, I've already have some definitions for what stress is. I know that stress is force per unit area. You know, that was one of our first definitions of the course. And I know that is the change in length over the original length. So if I have stress equals E times the strain, and I know that this is P over A, and I know that this is the change in length over the original length, well then I can just do a little bit of algebra and get that delta equals PL over EA. It's that simple. Just, you know, take this equation, multiply both sides by L, divide both sides by E, and there you go. It's that simple. Okay? So, you know, I don't want you to think there's any magic in how I'm getting this relationship. This is one of the most common formulas that we use in mechanics and materials. basically the relationship between how much load you put on an axially loaded member and how much it deforms. So it's a function really of four things, okay? It's a function of how much load we're putting on it. Obviously, if you put more load, it's going to stretch more. So again, when we say deformation, we're talking about how much it stretches. If I take a bar and yank on it, does it get an inch longer or 3 centimeters longer or what have you? So it's a function of how much load you put on it. It's a function of the length, because strain is changing length over the original length. The longer a member is, the more it's going to deform. So it's a function of its length. It's a function of E, the Young's modulus, the modulus of elasticity. Steel is going to deform differently than aluminum. And it's a function of the cross-sectional area. If I samurai sword or lightsaber through a tension member or a member subjected to axial load, the bigger that member is, the more oomph it's going to take to stretch it. So that's basically your four parameters that define how a member is going to deform when subjected to axial load. And that's basically it. Now, one thing that's worth mentioning is that formula is very nice and pretty only if the load or the area is constant, okay? And so what I mean by that is, what if you have a bar that's tapered? What if you have a bar where the if you have a bar where the area changes? Okay. Well, if the area changes, we got to break out the C word. We got to use a little bit of calculus because we don't have deflection as just a function of some constants. If the area is a function of x, then the deflection is going to change as well. So more often than not, we would need to integrate. Now, I want to show you something. This is pretty straightforward. All we're doing is we're saying, all right, we're looking at an individual element, and we're saying, well, that individual element can have some load as a function of x and some area as a function of x. So that's where we have this n of x and we have this a of x. Then all we're doing is just taking that and just integrating it over the length. Now let me show you this equation real quick. What happens if we have a constant length and a constant area? Well, if I have, an integral from x equals 0 to x equals L, and I have a constant load, let's call that n of x, let's just call that P, and I have a constant area, let's call that A, okay? How would I integrate that? Like, what's the integral of 7? Anybody? 7x. So if all of this is a constant, this P over EA, then the integral of that is that constant times x. So P over EA times the integral of x, or times the integral, which is x. And I evaluate that from x equals 0 to x equals L. So you remember, you plug in the top number minus plug in the bottom number, so you get PL over EA. So, bless you. I don't want you to think that this equation is magic or that it's coming out of nowhere. I mean, if your load and your area is constant, then it's pretty straightforward, okay? If not, if you have varying areas and varying loads, then you do need to integrate. More often than not, though, I don't want this to scare you, bless you, because in most scenarios, this is actually pretty straightforward. I've got two examples that I want to get through today. One of them is a little easier than the other. The other's a little bit of alphabet soup because there's a little bit of algebra thrown in there, but I'm doing it just to get you familiar with these expressions. The big point I want to get across is if your load and your area is constant, then you don't have to worry about all this calculus, just PL over EA. Sound good? All right. Now, I have an example here, and some of the parameters in this example are a little weird, and that's sort of on purpose. Like, for instance, I've got a bar that's 5,000 feet long. That's a bar, okay? But I'm doing that for a reason, because I want you to sort of understand some of the functions that we're going to use and how they're going to be employed. And I think the easiest way to do that with this problem is to use some parameters that are a little wonky, because I want to try and provide some reality to it, and I want you to have some intuition, okay? So what I have here is I have a bar, and it is being subjected to an axial load at the tip, okay? Now this bar is 5,000 feet long, okay? How many of you have ever, like, held, I don't know, like a piece of rebar that's only like a few feet long? Okay, now imagine holding a piece of rebar that's 5,000 feet long. That's pretty heavy, right? Okay, so the point I'm making is not only is it being subjected to a load at the tip, you know, sort of a load at the end, but the bar itself has a significant weight to it. If I have a bar and I just hang it from, let's say, the ceiling, and it's 5,000 feet long, that bar is being subjected to its own self-weight. So just under its own self-weight, it's going to want to stretch a little bit, okay? Now, how we determine that, we're going to have to break out some calculus, but I think you'll see where that's coming from. Now, I've got some parameters to throw out at you. So I've got the modulus of elasticity. It is 30 million psi. When you look at moduli of elasticity, if you're, for instance, in psi, it's not that uncommon to see like 30 million psi or 4 million psi. E values are high, so that's okay. The bar length is 5,000 feet. I have a yield stress of 59,000 psi. So remember, so this is a metal that has a yield stress of 59,000 psi. So that's when it starts to plastically deform. Y'all remember that? Remember that's when you get that little plateau in the stress strain curve. Now I have a bar weight. So the bar weighs something on the order of about every 6 feet it weighs a pound, so about 0.16 pounds per foot. And I have a bar diameter, and that bar diameter is 1/4 of an inch. Okay. So a couple questions right off the bat. Does the area vary? Remember, we use calculus when the load varies or the area varies. Does the load vary? No, it's a constant area, so we shouldn't have an area as a function of x. Okay, so that's point one. Point two, does anybody notice maybe a little bit of a hiccup that we might deal with in regards to these values? Units. I got units all over the place, and I am going to try and expose you all to both US and SI units in here. But regardless of what unit system that you're using, you have to use consistent units in your computations. And so in US units, you can mix feet and pounds and inches. You know, sometimes it can be pretty tempting to do that. So I'm going to right off the bat convert everything to a consistent unit system so that everything is consistent. All right. So, oh. All right. Example 5. So the first thing I'm going to do is I'm going to list some system parameters. I know it's early, but I'm going to get some nice. I am going to list some given values in all seriousness. I'm going to list some given values at the beginning of the problem. Okay? So the first thing that we were given in this problem is a Young's modulus, or a modulus of elasticity. So I'm going to say that that was E, and that is 29,000, or no, sorry, I'm thinking of different stuff. 30 times 10 to the 6, and that was, let me get that mouse cursor out of the way, PSI, okay? Now we were also given a member length, and that member length was 5,000 feet, okay? Right off the bat, you should see an issue, because I have pounds per square inch, and I have 5,000 feet. So before I do anything, I'm going to convert this to inches. So how many inches is this? 60,000 inches. So I'm just going to do that right now. Before I even start plugging and chugging into anything, just get it into a consistent unit system. And I'll tell you right now, when you're doing these problems, you know, that's how sort of the science works. You're going to be given some input, and then you've got to compute some output. Getting all of that input into a consistent unit system is worth it in the beginning. You're going to deal with a lot of your units errors head on if you just do that right at the beginning. Now I've got a yield stress of 59,000 psi. I'm going to call that sigma sub y. Okay. Now we were given a weight of the bar, and the weight of the bar was 0.167 pounds per foot. So what should we convert that to? Pounds per inch. And so how do I do that? Do I multiply by 12 or divide by 12? Divide. So what is this divided by 12? It's going to be small. So maybe like 0.14. Just keep it simple for our purposes. Do I have a second on that? There we go. All right, and I have a diameter of the bar of 0.25 inches. Obviously, inches. So far, so good? Now, let's look at each of the parts of this problem because I want to sort of figure out what's going on. Okay? The first thing it's asking is the value of Q to initiate yielding. Okay, so let's think about that for a little bit. Okay, how do we know when something has yielded? Like, are we talking about its deflection, its strain? Like, how do we know when something is yielded? What are we talking about when we think about yielding? We're talking about its stress, right? Okay, so when has something yielded? Well, it's yielded when its stress hits this, right? Okay, so how do we determine stress? Just simple, like basic. How do we determine stress? The load over the area, right? Okay, all right. Now, let's talk about the load over the area. There's going to be two things that generate stress, okay? Q, that load here at the bottom, right? So force over area, that Q. But there's another load on this bar that's going to generate stress. And what load is that? Its own self-weight. There we go. Now, here's what I want you to think about, okay? How long is this bar? What, 5,000 feet? Okay. Now, this is what I want you to do, all right? I want you to, this is the best you're going to get. I want you to imagine that you have really weird feet and that you have your feet right under this bar, okay? All right? And in your hand, you've got a lightsaber, right? Okay, that's horrible. I know. Okay? Now, you've got to cut this bar, right? When your secret weapon of engineering, you're cutting sections to determine forces, okay? What's going to hurt worse? When you cut right here or cut right here? That's going to hurt worse, right? Okay. Because if I cut here, that section is seeing less load than this section is seeing, right? Does that make sense? Everybody okay with that? Okay. I want you to think about that. I need to erase that travesty. So that was horrible. Okay. All right. So I want you to keep that in your mind, but let's keep in mind we're also talking about stresses. Stresses are defined as forces per unit area. What can we go ahead and easily compute right now? The area, right? We have the diameter of the bar, so let's look at part one. Let me head this. So we'll say load Q to cause yielding. So first off, we can compute the area. And this is a circular bar, so how do I compute the area? Somebody else. Right back there. We have a circular bar, so how do you compute the area? I know it's 8 o'clock in the morning. Area of a circle. Come on. Pi r squared or pi over 4d squared, right? We were given the diameter of the bar. Is everybody okay with this? So we have pi over 4 times 0.25 inches squared. And so what does that come out to be? They're like, it's 8 o'clock in the morning and we're in a meat locker. Do we really have to break out calculators? Yes, you have to break out calculators. You're engineers. Just be attached to the hip. 0.05. Let's add one more, like 0.49. All right, do I have a second on that? Anybody else got that? All right, okay. All right. Now, let's talk about that load a little bit. Okay, so here's the bar. Okay, and we've got that Q, right? That Q load here. And the bar is, what is it, like 60,000 inches long. Okay? What I'm going to do is I'm going to cut a section using my samurai sword or lightsaber through some random point. Okay? Through some random point right here. Okay? So let me draw that. So I've got this. I've still got my Q. And here's my cut. All right? And I've cut it through some random distance. So this distance here is X. Everybody okay with this? Now, this bar weighs, I'm going to use feet because I think it's a little easier for our discussion. The bar weighs 0.167 pounds per foot, right? So let's say I cut through the bar and that distance is 1 foot. How much does the bar weigh? Like, let's say that this is 1 foot. How much does that little piece of bar weigh? It's going to hit you on your foot. 0.167 pounds. Okay. What if it's 100 foot? It's 0.167 times 100, right? Make sense? So the longer this X portion is, the more the weight is. And how do you determine that weight? You take the weight of the bar times X. Make sense? So here's what I propose. I propose that this little bar piece is experiencing two forces pulling it down. This Q, whatever that is, and it's also experiencing kind of like a distributed load. It's experiencing this sort of weight of the bar that's pulling it down, and that's a function of X. I propose that if you cut that bar, it's going to fall. Why is it going to fall? Because there is some internal normal force holding it up. Okay? And if I sum forces in the y direction, I propose that that normal force is Q plus whatever that weight is, or what the weight of the bar is, times whatever X is. Does that make sense? Is everybody okay with that? Or is that too much for 8 o'clock in the morning? Everybody good? So, let's ask a simple question. When is your foot going to hurt the most? When you cut right at the very top, right? That's when your foot's going to hurt the most. So I propose that right at the top is where the bar is seeing the most load, right? Okay? So if that's where it's seeing the most load and the area is constant, that's where it's going to see the most stress. So let's figure out what the maximum load is. So I propose that, therefore, P max is the load at, we'll say X equals 60,000 inches. So that is Q plus 0.014 pounds per inch times 60,000 inches. And so that's Q plus what? I'll make y'all do some work this morning. You could also take 0.167 times 5,000, just as long as your units are consistent. That's all that matters. Say it again. 840. Is that what you got? Do I have a second on that? So what you're telling me is that the bar itself weighs 840 pounds. Now, we don't have a clue what Q is because that's what the problem's asking for. It's saying tell us what Q is so that yielding occurs. Okay, so let's see what that is. If that is the maximum force in the bar, how do I determine what the maximum stress in the bar is? Well, no. This is the, yeah, well, that's ultimately what we're going to do. What I'm asking is, that is the force. How do I calculate what is the stress? I take this and do what with it? There we go, divide it by the area. So if that is the maximum force, the maximum stress is that divided by the area. So Q plus 840 pounds over 0.049 inches squared. Now we do what you said. We said our goal is to try and figure out what is Q so that yielding occurs. Well, I take that maximum stress, I set it equal to sigma y. So Q plus 840 pounds over 0.049 inches squared, that's got to equal 59,000 psi. So Q plus 840 pounds equals 59,000 psi times 0.049 inches squared. So Q is 59,000 psi, 0.049 inches squared minus 840 pounds. First off, do my units work out? Yeah, I got pounds per square inches and inches squared, so everything works out there. What does Q come out to be? 2,051, is that what you said? Do I have a second on that? All right, so 2,051 pounds. Okay, we'll say that's the answer to part A. So does that make sense? That's how much load is required at the bottom to cause yielding. Anything more than that, this section is going to yield and freely deform. What do you think? Any questions? All right. So if you're okay with that, now let's look at the second piece. Okay. The second piece is asking for what is the total deflection of the bar under that load. Now, we would love to be able to use PL over EA, okay? But we can't, okay? We can't use that for one reason. What's that? Remember, we can use PL over EA if the load is constant and the area is constant. Can we? The load's not constant, the load varies, okay? So because the load varies, we can't utilize that, so we have to integrate. But fortunately, the integration is pretty simple because we've already done the hard part. The hard part's actually not the integration. The hard part is determining our load. We've already done that, okay? Here's our load right here, this N of X. This right over here, this Q plus W bar X. This was the hard part. Once you've got that, everything else is pretty simple. And I'll show you how that works. So, does everybody have all this? Am I good to go on the next panel? All right. Okay. So. Okay, so the deflection, that's a little lowercase delta, if you're curious. So that's an integral from x equals 0 to x equals L of N of X divided by E A of X dx. Okay? So I'm going to test your Calc 1 skills. Don't worry. By the way, we do see some calculus in this class, but usually calculus is incredibly simple. If you know what like the derivative of x squared is, you're pretty good. So let's start filling this in. Now, area is constant, right? So what I'm going to do is I'm going to factor out the area, and I'm going to factor out this E value. Okay? So 1 over EA. Then we have the integral from x equals 0 to x equals L. And what was in? It was Q plus W bar x. Right? That was simple, right? So 1 over EA, and let's integrate this out. What is the integral of Q? QX, okay? And what is the integral of this W, bless you, bless you. What is the integral of like WX? Remember, W is a constant, right? So we pull that out, and the integral of x is x squared over 2, right? So we've got W bar over 2 x squared. Now this is a definite integral, so we got to evaluate that from x equals 0 to x equals L. Fortunately, that's pretty simple. Remember how that works? You plug in the top number minus plug in the bottom number. If I plug in the bottom number, what am I going to get? 0. So all I'm going to do is plug in the top number, and I'm going to say, all right, we've got 1 over EA, and then that's QL minus WL squared over 2. That's it. It's that simple. So far, so good? Yes, sir. Oh, no, that's plus. That's plus. Sorry. Remember, Marshall University policy states that I'm allowed to make 7 mistakes a semester, but I'm only going to count that as 0.1 mistake. I count the mistakes, so I know it's really one side. It doesn't really work out. It was a joke, not a very funny one. All right. So let's go ahead and plug and chug. So over here on the outside, we've got 1 over, and we've got a bunch of stuff. So E, what was E? It was 30 times 10 to the 6 psi. What is A? I don't remember. 0.049 inches squared. And then Q, we're using the load that we got from part 1. And so you said that was 2,051 pounds. Okay, the length is 60,000 inches plus, then we have, this is 0. What was the weight of the bar? It was like 0.14, something like that, pounds per inch. And then 60,000 inches squared over 2. So let's see what you get. And just so you're aware, you're going to get a pretty long deflection for this example. That's the one thing about this example. The deflection comes out pretty high, and that's usually not normal for a lot of the problems that we do in here. But I thought that the 5,000 foot long member would make that make a little more sense. Anybody have a deflection for me? Like I say, it's pretty high. It's okay. While you're computing that out, I know sometimes it might seem like a lot of work, but actually write out the units so that you know everything matches. Pounds per square inch, square inches, pounds, inches, pounds, inches, inches. Make sure that you write all that out. It will make your life easier down the line. Anybody got an answer for me? Anybody? $255. Anybody else get that? Anybody? Hello? Anybody got a number? I didn't get 255. I got something else. I got 100.86. Do I have a second on that? There we go. So that's 100.86 what? Inches. There we go. Remember, if you've got questions, please, it's okay to ask. And if there's anything you're unsure about, ask now. Like, I'd rather you ask. And here's another little secret that us professors don't tell you. This happens quite a bit. Somebody will have a question, and they're brave enough to ask and say, hey, I have a question about this. And as soon as they ask, I get like 4 or 5 other people like looking at me like, yeah, I wanted to ask that question too, but I didn't want to be the person to ask it. Guarantee if you have a question, there's probably other people that have a question too. So don't be afraid. This is your time. Y'all are putting money on the table to be here, so. Yeah.
I do have a question.
Sure.
Whenever you get to like a point in a material where it starts to strain harden, wouldn't your modulus of elasticity be changing at that point?
That's a good question, and I'm going to repeat for the recording. The question was, if you get to a point when your material strain hardens, doesn't your Young modulus change? The answer is yes. I mean, the slope of your curve changes. For our purposes and for just about every purpose for most purposes in engineering, we don't like that to happen. We usually like to keep everything in the linear range. That's not always. I mean, there are some instances where yielding is desired, but for our purposes and for most engineering design, we want everything to stay linear. So we want to keep it in the linear range. A lot of our problems are going to focus around things like how much load would cause it to yield, or is it going to behave elastically or not? So that's a good question. That's a good question. Everybody else okay with that? And it's you? Okay. Any other questions? This is good stuff. All right. Okay. We're at 69 degrees in here, so it's starting to warm up. Maybe the room knows that we're talking about thermal expansion later. I'm going to get you all laughing. It's going to happen. All right. Now, I added a little note to this problem, so if some of you have your slides and whatnot printed out, you're not going to see that yellow box, but I did that this morning. And this will make some sense as we go through this, so just bear with me. So I have a bar here. Now, this problem is a little different than the one that we did for the previous problem. This is a little different, okay? This bar is tapered, okay? So is the area constant on this problem? No, okay? But is the load constant? Let's say, yeah. If I cut a section here, I got P this way, I got to have P that way. If I cut a section here, I have the same thing, okay? So far, so good? All right. Now, that's one sort of glitch that we're going to have to deal with in this problem. Another thing that we're going to have to deal with in this problem is that there are no numbers. I don't like to do this a lot. Most times I won't. In most cases, I won't ask you to derive anything symbolically. But in all seriousness, there are a few instances where it is incredibly necessary and valuable for engineers to have symbolic formulas for stuff. One very common example is when you're designing beams. Beams can be subjected to all sorts of different loads and all sorts of different ways. And depending upon the type of loading that you have and the geometry, you can get different beam deflections. And so it's very common for engineers to have a reference where it's just beam deflection equations. Like, here's my load, here's my deflection. And so you have to derive those symbolically. So they are quite useful. I don't like doing this stuff just to make your head spin. But I want you to understand there's a reason for it. Now, What I'm also going to do in the example, just so you're aware, is I'm going to start off by just guessing some numbers. And I'm going to do that so that you all can have a little bit more intuition as to what's a constant, what's a variable, and so on and so forth. Okay? Before we get into the example, there's one thing that I want to indicate, and that's that note. What we're going to do for this problem is we're going to assume that the area, we're going to assume that the area of the bar is what varies linearly. Okay? Now that's technically not true if you look at this. I know it may seem like it's true, but it's not the area of the bar that varies linearly. It's really the diameter that varies linearly. Okay? For our purposes for this example, I want to assume that the area linearly varies, and then I think you'll see how we would handle the diameter varying. And it's the only difference between the two is just a different integral, and you'll see why. So let's just get into it. Okay, and I'll try and be pretty, I don't want to say verbose, but I want to make sure I'm being clear on my notes. Like I said, most cases I'm not going to give you all a full-blown symbolic problem. I try and avoid that as much as possible. Okay, so let's see. Which way was it? Facing that way. Okay, so we've got some load P, and one thing we do know from the problem is we know that we have a dA we have a dB, and we know that this is L. Okay? Okay. So far, so good? Now, to begin this problem, and this isn't going to be how we ultimately answer it, but I just want to throw some numbers at it so that we can have some reality and a little bit of, be a little grounded when we have our discussion. So I'm going to say to begin, let's assume some values. All right, so I'm going to assume, just for the sake of discussion, that the diameter of A is 1/2 inch and the diameter of B is 1 inch. We'll say that this bar is 5 foot long or 60 inches long. We'll say that P is 20 kips. And then we'll say that E is 10,000 KSI. Now these are all pretty reasonable assumptions for values for a problem like this. But the main reason I want to do this is because when we start doing some calculus later and start doing some derivation, some integration, I want you to have a very clear understanding as to what is a number and what is a variable, okay? And I think the easiest way to do that is just to throw some numbers at the problem and see what happens, okay? So if we've got these, 6, yep, 0.15 mistakes, all right? So if I've got diameters, would it be intuitive that if I've got diameters, I could say we can easily compute areas at the ends. So the area at A is pi over 4 dA squared, and the area at B is pi over 4 dB squared. So if we plug and chug, What are we getting for each of these? What's that? Well, I mean, give me a decimal. Y'all are engineers. We can go with decimals. We don't need all that theoretical stuff. What are we getting for the first one? We'll make y'all do some math this morning. Oh, the pi. But I got a first one. Say it again, 0.196. Do I got a second on that? All right, what about the second one? Somebody in that back row, I'm calling y'all. 0.785 inches squared. Break y'all out of your shells. All right, so far so good? So the point I'm making is when I refer to areas at either end, they're numbers, right? So I just want you to think about that, okay? Now, let's continue, okay? For this problem, we're assuming that the area varies linearly. Keyword linearly. It's a line. What's the equation of a line? Y equals mx plus b, right? Okay, so let's think about that. All right. Now what I'm going to do is this. I'm going to define myself a coordinate system. Okay? Okay? So this is the area at A. This is the area at B. Okay? Now, this is a coordinate system, right? So if the coordinates of this point, let's say, are x equals 0, what are the coordinates of that point? X equals L, or x equals, I don't know, 60 inches or what have you, right? So I propose that we've got 2 points, okay? We have 0, AA, and we have L, AB. Is everybody okay with that? So if you've got that, now I'm not telling you how to determine the equation of a line. You're going to tell me. So if you got 2 points, I need the equation of a line. What do? Y equals mx plus b. So what's m? And I know that. How do you, come on, let's ignore the mechanics. Just basics. There you go. Change in y over change in x. All right? So AB minus AA over L minus 0, or just AB minus AA over L. Now, I'm not going to compute this out, but help me out. Is that a number? That's going to be a number, right? Because that's a number, and that's a number. So it's a constant, okay? All right. Y-intercept. What's the y-intercept? You're right. So what is that value? It's AA, right? Remember, the y-intercept is where x equals 0, so that's this, right? So therefore, I propose that the area of x is mx plus b, where m is that and b is that. I'm going to circle that because I think that's kind of important. What do you think? Are there any questions about that? That's kind of important. All right. Everybody good? All right. So there's that. There's our area. I'm going to put for our load. Can anybody tell me what that's going to be? Not you. Somebody else. What is this going to be for our problem? Somebody up here. What's our load going to be for the problem? Like, does it vary or is it constant? It's constant. So it's just going to be P, right? There's nothing that varies. Does that make sense to everybody? All right. Okay. Everybody okay with that? If you're okay with that, then we can start doing some number or some integration. Can I go ahead and skip ahead to the next sheet, or are you all good here? Or you need me to wait for a second? Good? Okay. All right. All right. So, therefore, for our deflection, okay, we've got n of x is P, but we have a of x is our line, mx plus b. So therefore, our deflection, we integrate from x equals 0 to x equals L, n of x over e a of x dx, right? And just start plugging and chugging. So integral from x equals 0 to x equals L of P times e over mx plus b dx. So what's a constant? What can I pull out? The P and the E, right? So the P and the E, integral from x equals 0, x equals L, dx over mx plus b. All right. Does anybody remember how to do that? You've got a natural logarithm in there, that's for sure. All right. What's that? Well, let's do this. Let's take it step by step. Okay. Let's do this. Let's say let u equal mx plus b. Okay. So what's du? It's m dx, right? So why don't we say this? We have P over E, x equals 0, x equals L. All right. The mx plus b, let's call that u. And then the dx, we'll call that du over m. Right? So I got an m over here on the outside. Integral of x equals 0, x equals L of du over u. And so now that integrates as the natural log of u. Now we still evaluate that from x equals 0 to x equals L. So far so good? All right. We replace our u with mx plus b, right? Now how does that work? You plug in the top number minus plug in the bottom number, right? So natural log of ml plus b minus natural log of b. Did I do that right? All right. And remember, now let's go back to logarithms. If you've got log of a minus log of b, you can turn that into a fraction. So we have p over em times the natural log of that. Everybody okay with that? So I propose then that our answer is delta equals P over EM natural log of ML plus B over B, and M is that, and B is that. What I highly suggest that you do is this. Remember those numbers I sort of made up at the beginning? If you plug and chug those numbers for this problem, what I highly suggest you do is chug that out and say for our data, you will get a deflection of about 0.282 inches. I highly suggest that you do that just to make sure you're comfortable with this. Now, I will admit that this example is a little more on the difficult side, so if some of the alphabet soup and whatnot you got lost in, that's okay. I just want you to recognize that there's multiple situations that can occur. You can either have a load varying or an area varying. For our purposes in this problem, we said that the area varies, but really that's not the case. Really it's the diameter that varies. So if you were to do this problem and assume that the diameter varies, instead of having area equals mx plus b, you'd have the diameter equals mx plus b. And then to compute the area, you take pi over 4 times that squared. So you got to FOIL that and then integrate that. It's not like it's harder, it's just more stuff, and it was sort of outside the scope of what it is that we cared about. Is everybody okay with this? Any questions? All right. Now don't worry, I'm not going to keep you here too much longer. We've had a pretty heavy day in terms of math, and what I want to do is introduce a concept for next week that ultimately I think is going to be a little more interesting and a little more fun. Lot less calculus and stuff like that. We're not going to be dealing with much more of that, but the challenge and the understanding is going to pop up. Okay? What I want to do is introduce to you the concept of indeterminacy. Now, if you have me for structural analysis this semester, we've already talked about it in there, okay? But we haven't really dealt with it in there. We've defined it and we've taught you how to identify whether or not a structure is determinate or not, but that's it, okay? We won't handle statically indeterminate structures until later. For our purposes in this class, though, we actually are going to start handling indeterminate structures right now. Although it's going to be a little more localized and kind of on a member-by-member basis, whereas for you civils and structural analysis, we'll be looking at indeterminate systems, so it's going to be a little bit of a bigger deal in there. But the way I want to introduce it is I want to look at this structure, okay? This is a 2-bar truss, okay? What's 2 ways you can solve a truss? I know you all remember this, right? We have method of and method of sections, all right? Let's talk about the method of joints, okay? So let's say I'm utilizing method of joints to solve this joint. How many unknowns do I have? For this joint right here, I only have 2. I got whatever's in this member and whatever's in that member. Is everybody okay with that? Now, I mean, I see what you're saying if you don't know what that force is. Let's say I told you that force was 300 pounds, okay? Then the unknowns would be whatever's in here and whatever's in here, right? Now, when you do method of joints, you have 2 equations of equilibrium. See, all the forces all meet at a common point. So you have sum of forces in the x direction and sum of forces in the y direction, okay? This structure would be a structure that we would consider to be statically determinate, okay? What I mean by that is you have 2 unknowns and you have 2 equations of equilibrium. And when that happens, all you need is equilibrium to solve the structure, okay? What if I do that? Okay, what if I add another bar to the system? Okay, now I've got 3 unknowns. Okay, This is a structure that is statically indeterminate, okay, where there are more unknowns than there are equations of equilibrium, okay? Now, this might seem like a really complicated example of indeterminacy, but we are going to handle some very real examples of indeterminacy very soon. For instance, this may not look it, but that is an indeterminate member because it's what's called a composite member, a composite column, because there's a member that's made of two materials. So the question is, how much stress is in each material? And that's not that easy to determine, and it's impossible to determine without compatibility relationships. Now, a compatibility relationship is basically saying that when it's all said and done, once you apply this force to this structure, it's going to deform, right? We're in mechanics of deformable bodies because we recognize that everything is deformable. When you apply a load to something, it will respond by deforming. Compatibility relationships basically say that once you apply this load, this point right here, it'll deform. Let's say it moves down there. Compatibility relationship says that all of the members basically kind of have to deform the same way. So this member might get a little shorter, this member might get a little shorter, this member might get a little shorter, but ultimately they all have to get short that perfect amount so that they all meet at the same point, okay? Now geometrically that's a little tough on this problem, but on this problem it's pretty simple. Okay, and I'm using this example just for discussion purposes. We're not going to do any math today, so you all can put the calculators on. Oh, thank God. We don't want to do any math. We got dynamics in a little bit. We're like, you know, having to gear up for that. I know things. I want to take a look at this member just for discussion purposes. Okay, this is a composite member. Okay, so specifically, I have an aluminum surrounding, so it's basically an aluminum pipe, and inside it is a brass core. So the column is made of materials, aluminum and brass. Okay, aluminum and brass have different Young's modulus, different modular elasticity. So if I were to apply the same load to those pieces separately, like if I had the aluminum part here and the brass part here, and I put 9,000 pounds on either of them, even if they're the same length, and even if they're the same area, which they're not, but even if that were the case, they're going to respond differently because of the different E values. They're going to deform differently, okay? But not here, not in this case, okay? In this case, because it's a composite column, when I push down on the top of that column, I'm going to deform both of them at the same time, okay? So I'll make up a number. Let's say that the deformation is 1 inch. When I push this down, they both deform 1 inch. Okay? So the question is, well, how much force goes into the aluminum and how much force goes into the brass? Okay? That's actually indeterminate. Okay? Because if I take a samurai sword or a lightsaber and I cut through that, I have one force going down, whatever that P is, but I have two forces going up. I've got whatever force is in the aluminum and whatever force is in the brass. But if I sum forces in the y direction, I only have one equation of equilibrium, but I got two unknowns. That's indeterminate, okay? How do I solve that? I need another equation. I need something else, another fact about that system in order to solve it. And I propose to you what that fact is that they both deform the same amount. The deflection in the brass equals the deflection in the aluminum. And that's what compatibility is all about, okay? There are two types of indeterminate problems that we deal with typically in these types of scenarios. One of them is what's called internal indeterminacy. An internally indeterminate structure is like a composite member, where, you know, we could solve for reactions and whatnot all day long, but the indeterminacy arises from the composition of the member itself. This member is comprised of two different materials, one made of aluminum and one made of brass. So that's where the indeterminacy comes into play, and that's internal. This is a little bit more on the external indeterminacy side, where you could solve for each member internally, but it's the external forces that give you a little bit of grief. Here's a Here's another example of external indeterminacy where, if I had a load, let's say, applied to this bar, it's only one bar, it only has one area and one length and one E value, that's fine. But just looking at it from an external point of view, if I put a load this way, there's two support reactions. So how do we determine the forces, how do we determine those support reactions in a scenario like this? Well, in this scenario, we look at deflections as well, but we look at it a little differently and we ask ourselves, well, what's the deflection right here? And what would the deflection be right here? If this is a support, if this is resisting those loads, what's the deflection? How much does this point move? Well, not if it's restricted. That's the point. What's the deflection? It's 0, okay? So for internally indeterminate structures like this, we'll recognize that they both deform the same amount, okay? But here's the easiest way to look at it like this. If I take this column and I press load on it, would you agree that the column's going to get shorter? It's going to squish, right? Okay? But I'm also saying that this is pushing back. So I'm saying that this point doesn't deflect at all. Does that make sense? So internally indeterminate structures, we're going to use that internal compatibility. But for external indeterminacy, we're going to say that those external supports don't deflect at all. And we're going to use that relationship between loads and deflections in order to determine what are the forces and stresses in each of those components. Does that make sense? Everybody okay with that? Don't worry, we're not going to get into any of that math today. That is for after your long weekend. After your long weekend, you get to come back here at 8 o'clock in the morning. I can see you all are having an extremely hard time containing your excitement all over it. Everybody good? Any questions? Any questions about your homework? It's due Tuesday. All right. I will see you all next week. You all have a wonderful weekend. Yes, yes.